So the question was about the ratios in mass spec. How do you know what's what and what you're looking for? So I'll just draw a generic mass spectrum so that we know what the terms mean, so we're all on the same page, and then I'll put the 4 different scenarios of what you need to consider. So halogens and mass spec, again, like pretty much every piece of data, there's normally 2 axes. The x-axis is mass to charge, and that's typically indicated with m to z. For what you guys are learning, z is always 1, so the charge is always 1. That does not necessarily have to be the case. If you're looking at large like proteins, the charge can be like 8 or higher, and so it makes the math a little bit more complicated. But because z equals 1, on the x-axis you're essentially looking at the mass only. The y-axis is relative abundance. So this is usually in a percent. So we'll say this axis is 0 to 100%. And again, the mass axis will start at 0 and then go up to essentially infinity. So we have from the periodic table, those are your halogens. Fluorine is 100% abundant. So what does that mean? You're not going to see anything special if the molecule does contain fluorine. So it's sort of, you have to determine it some other way, and that's not the most satisfying answer, but what you're basically looking for is if it has chlorine or bromine or iodine. So fluorine's out. Chlorine has 2 isotopes, 35 and 37 Cl, that occur in a natural ratio of 3 to 1, or what's that, 75-25. So that's just the normal isotopic abundance of that stuff in Earth. So what does that look like if you were to see a parent? The parent is the ion that has the highest mass, and that is the mass that contains every element of the molecular formula. So just estimating here, that's like a 3 to 1 ratio. The parent is typically called M, and the plus means that it's an ion. Mass spec will only detect an ion. So ions can be plus or minus. You're probably asking, okay, what doesn't it detect? It does not detect radicals, which are unpaired electrons. So you'll learn about radicals at some point in this semester. The other thing it does not detect are called carbenes, which are also neutral. So the parent is the ion that has all the elements in the molecular formula. So what does bromine look like? There's 2 isotopes of bromine, 79 and 81. And these occur in a 1-to-1 or 50-50 ratio. So just to backtrack a little bit, I called that parent M+. The plus is the charge. So there's 2 lines there. So the other line we can say is M plus 2 plus. So hopefully that doesn't confuse you. The plus 2 just means that would be like the molecule that has chlorine 37 in it, or bromine 81. It's just 2 mass units higher. So iodine is 100% abundant. So like fluorine, it's really not indicative. The only thing you would see is a peak at 127. And that corresponds to the iodine atom itself, I+. So it's sort of out in no man's land at 127. So mass spec, if anyone wants to go into any sort of analytical chemistry, is pretty powerful. The job that I used to work in, we would take compounds and label them with carbon-14 or tritium atoms, which are radioactive. So with carbon-14, you get an M+2 signature, and it's radioactive as well, so you can detect the disintegrations. And drug companies use it to track metabolites in rat, dog, or monkey. So how you feel about that in terms of how drugs are developed, they are tested on animals, and lots of animals. So they test the metabolic pathways to make sure that the drug is not forming a toxic metabolite. So when you take something, it has the desired effect, cure whatever, but your liver is also doing chemistry on that molecule. If it transforms it into substance B and that's toxic, you die. So they use animals to figure out if that's going to happen or not. And so the mass spec is pretty important for figuring out exactly how these things get metabolized. So hopefully that answers your question. Really what you're looking for in terms of the mass spec are these two things, and it will really be a visual sort of thing at the parent. So you have your M and then your M+2, whether it's a 3-to-1 ratio or a 1-to-1 ratio. Look in this Klein book real quick to see if there's something problem we can do. Maybe one other thing I want to point out. If you have an odd mass, that's typically equal to, like, say, 1 nitrogen or 3 nitrogens or 5 nitrogens, so an odd number of nitrogens. So that's another, something to look for, dead giveaway. Next question. Hopefully the projector doesn't overheat. Yeah.
You have this handout, looks kind of like this, if you can see it.
Yes.
Can you explain what is up with that? I was sick when you went over it, so
So the question was about the handout with the 2D spectra. So I have 2 of those prepared. Let me just do a problem from the book real quick that presents the data in a different way. Then we'll get into those other COSY, HSQC, and HMBC. So let me put some stuff down, and then we'll sort of put it all together and discuss. So this is from your Klein book. 15, chapter 15, problem 61. So I'll give you everything that they're writing here, which is like more information than I would give you. So you'll be able to, I think, get this pretty quick because there's a lot of clues here. So it says determine the structure of an alcohol. So if I was taking this exam, I would write down alcohol. I would then write this down. That's what you need for an alcohol is OH. With the molecular formula, so they're giving you that C4H10O. So how many degrees of unsaturation do you have in there? So 0 degrees of unsaturation. And so why is that important? So there's no pi bonds, there's no rings, there's no sp2 hybridized carbon, there's no sp hybridized carbon. So maybe, I don't know how other professors instruct you or how they tell you how to solve problems, but there's like positive data you're getting that you can work from, and then there's things you can infer. So in this class, the more you can infer things and set a boundary about what a structure can be, it helps you arrive at the right structure a lot quicker. So there's a couple things, and we could even do this a couple ways. We could just right now draw every possible isomer there is, and then I can give you the data, and then we can figure out which data matches those isomers. So that's one way of doing this. That's pretty easy. But I'll just give you the data and see what you come up with. So here's the data, and they use this word, broadband decoupled. That's a fancy word. Broadband just means it's the carbon from 0 to 220 parts per million. Decoupled means every carbon peak looks like a single peak. You don't see any sort of splitting associated with it, so just a normal carbon.
What was the number range for broadband again?
0 to 220 parts per million. So you're starting with 4 carbons, and they're telling you the data has 4 unique carbons, so there's no symmetry in this molecule. Otherwise, the number of peaks you would see would be less than 4. Okay, before you bite my head off about what these numbers mean, so the depth experiment is telling you the classification of those carbons. The number after the depth tells you how the pulse sequence hits the nuclei. So 90 basically tilts the nuclei 90 degrees, 135 tilts at 135. Is that important to you? No. What's important is if it tells you if the phase is up or down. So 135 says there's positive signals at 10, 22.8, and 69.3. So those are phased up. It has a negatively phased signal at 32.1. So our key was CH2 is phased down, CH3 is phased up, or positive. So what does the depth 90 do? It basically takes change the marker color here. Takes this information here, which is sort of ambiguous, right? You have 2 signals that are phased positive. The 90 differentiates between those 2 and only tells you the CH. So it phases the CH positive, and in this one, that signal is 69.3. So what it's telling you at this point is that this peak here is a CH. So you've differentiated them. You have two CH3s, one CH, and one CH2. Does everyone follow that?
Could you go into how the 69.3 is, like how the 90 makes it?
So what NMR does, NMR is two things. It's a magnetic field in which the nuclei reside. The nuclei are either going with the magnetic vector or against it. So the other part of that is the radio frequency, which is the operating frequency. So on the Spectra you have, it'll say like 200 megahertz or something. So that's the radio wave that's hitting the spin of the nuclei, and it's flipping it whatever angle. So either 135 or 90. In this experiment, 135, you differentiate the CH2s because they're pointed down. But that doesn't differentiate CH and CH3, so it's still unknown. So this other sequence takes these two and only gives you the CHs. So because it's only listing the 69.3, you can assume that these other two are CH3 groups. So if you plunk all these fragments together, we said we have CH3, CH3, and again, that's from this piece of data right here. This is a CH. That's a CH2. And you have an OH in there because they gave that to you. So you have to put all those things together. You have to use them all. So you can't just bond two things together and leave two other fragments. It's like putting together a piece of furniture. You can't have like 5 screws and 3 nuts left over. You got to use everything. So when you do that, if you know the name, say the name and I'll write it. So 2-butanol. Does everyone see how we arrived at that? So what you can do is, I haven't really formalized this in my brain, so what I'm about to say may not be true. You could start with the thing that's the most, maybe not most, the least substituted, the CH group, and start plugging things onto that. So if you plug the OH group onto that, so you would get this. So you've used those fragments, then you have those remaining things left. I would then go to the CH2 next. And then you're left with 2 things on that fragment and then 2 methyl groups. So we just plug them in there, and that gets you something that will not violate any Lewis dot conventions. So this should make sense to you that that peak there is the 69.3. That's the only one bonded to a heteroatom, so it has the furthest chemical shift away from 0.
For the test, do we need to be able to like, look at that and tell, or be able to know that it's the 2-butanol?
In terms of what exact question are you asking?
Like, I guess, do we need to know how, like, the name of my
Would you need to know that name? Not for this exam, but I think you could be able to figure that out. You know what I'm saying? I don't want to like discourage you.
Or just like, brush up on it, but like.
So you need to know like 1 through 10 what those parent carbon names are.
Right.
And then the substituents so far have been sort of straightforward. But
Yeah, I was
there's
a little bit confused when putting it on first started off.
Okay. So just to review that real quick, and then we'll get to that other spec problem. So anytime you name something, like this structure, if you were just given that structure, you circle the longest carbon chain. So there's 4, so that's a butane derivative. And then you number it such that any substituent hanging off or outside that circle gets the lowest number. So this is 2-butanol rather than 3-butanol. So we'll go through this in a couple weeks, but I mean, the naming isn't terribly difficult. I have like 20 iClicker questions we'll go through to learn naming. Yeah.
Quick question on that specifically. It gets the null because of the alcohol, right?
Yeah, so I think I've said this to a couple people. In Western philosophy, we're taught to read like left to right. And that's how you would read that name, 2-butanol. If you had to take 2-butanol and then draw it, really what you're doing, you're looking for certain parts of the molecule. The parent chain is the number of carbons, so that's butane. We've dropped the E, and this OL tells you the main functional group is an alcohol. So alcohol ends in OL. The parent of an alcohol ends in OL. So really you're dissecting it here, and then this number, which is called a locant, tells you the location of the OH group. So what I'll do, I'll go into this a worksheet here, and we'll talk about these 2D things. Step 90. Whoop.